In part 2 of this introduction to redox chemistry, we're going to have a look at using oxidation numbers to track whether things are being oxidized or reduced, whether they're acting as oxidizing agents or reducing agents, and then have a look at a little bit of work on half reactions. So let's start by having a look at this reaction. We're going to track what happens to iron, Fe, during the reaction. And the key learning point here is if something is going to be oxidized, then its oxidation number will become more positive. Now, we use more positive specifically because it could, for instance, go from -2 to -1, and that's also becoming more positive. Reduction, then, we will notice something is reduced if the oxidation number becomes more negative. And once again, it could be something simple like going from -1 to -2. That's obviously becoming more negative. But even something going from +3 to +1 also is becoming more negative. So let's have a look at Fe in this reaction. Let's track oxidation numbers. Chlorine is -1, and there are 2 of them, so that's -2, which means that our Fe is +2. And on this side, chlorine still is -1, there are 3 of them, so that's -3, so our Fe must be +3. So iron on this side's gone from +2 to +3 on this side, and if we have a look at our definitions, +2 to +3 oxidation numbers become more positive, and therefore iron in this case has been oxidized. Let's have a look at another example. In this case, we're going to follow the chlorine and see what happens to it. On this side over here, chlorine is a diatomic molecule, but it's an element. It's not combined with anything else, and so its oxidation number is 0. On this side over here, potassium is +1, which means that chlorine is -1 because it's a neutral compound, and so chlorine has gone from 0 to -1. It's become more negative, obviously, more negative, which means that our chlorine has been reduced. Alright, go to your notes now, and you'll see that there are a couple more examples, as you see on the screen now, and in each case try and track what happens to the particular element. In the first one, you're having a look at manganese. In the second one, you're having a look at sulfur, and in the last one, you're having a look at iodine. So in each case, have a look at its oxidation number on the left, oxidation number on the right, and then use our definitions to work out whether it's been oxidized or reduced. So stop the tape now, go ahead and try that out, and then you can play it and check the answers. Alright, now that you've had a go, check your answers against my ones. MnO2, oxygen is -2, and there are 4 of them, so that's -4, which means manganese on this side must be +4. On this side, we've got 2 Cls, each -1, so that must be -2, which means that manganese must be +2. And so manganese has gone from +4 to +2, therefore it's become more negative, or positive. The amount of positive charges decreased, and so that is a reduction reaction. Manganese has been reduced. Let's have a look at sulfur. Hydrogen is +1, and there are 2 of them, so that's +2. Oxygen is -2, and so that's -8, which means that our sulfur here must have been +6 on the left. And on the right, here's sulfur, 2 hydrogens, that's +2, which means that sulfur must have been +2, so that must be -2. And so sulfur's gone from +6 to -2, also clearly been reduced. So in this reaction, sulfur's been reduced. And then finally, iodine. Potassium's +1 because it's in group 1. 3 oxygens, each -2, so that's a total of -6, which means that iodine here must be +5. On this side, potassium +1, group 1, oxygen -2, which means that our iodine, sorry, that's +1 on this side, +1 and -2, which means that our iodine must be +1 to give that a neutral compound, a total of 0. So +5 down to +1, again clearly reduced. So in each case, you can see those are examples of reduction reactions in terms of the elements that we've been following: manganese, sulfur, and iodine. Right, we're now going to use oxidation numbers to try and work out what's acting as an oxidizing agent and what's acting as a reducing agent. This can be a little tricky, so you need to keep your wits about you. Let's start by writing this as an ionic equation. Copper oxide, we have Cu2+. We have O2-, but we also have O2- on that side, so the oxide ion is just a spectator ion, so I'm going to leave that out. So our Cu2+ reacts with magnesium to form Cu, and on this side we've got Mg2+, and then the oxide ion, which I'm leaving out. Now if we have a quick look at oxidation numbers, you can clearly see that copper there is +2, whereas on this side it's just an element, so it's 0. Magnesium on this side is 0, and on that side it's +2. So our copper has gone from +2 to 0. The oxidation number has decreased or reduced or become more negative, and so that's an example of a reduction reaction. The magnesium has gone from 0 over to +2, so the oxidation number has increased or become more positive, and so that is an example of an oxidation reaction. So our copper 2+ has been reduced to copper. Our magnesium has been oxidized to Mg2+. So copper 2+ has been reduced, therefore magnesium is the reducing agent. That's what caused the copper 2+ to be reduced. Our magnesium itself was oxidized, and what caused it to be oxidized was the copper 2+, so that is the oxidizing agent. So the species that is reduced is the oxidizing agent. The species that is oxidized is the reducing agent. Alright, let's have a little look at some half equations now. We're asked to write a balanced equation for the reaction between iron 2 ions and chlorine to form iron 3 ions and chloride ions. So let's start. Iron 2, that's Fe2+, and that's reacting with chlorine. Notice the ending INE indicates that it's elemental chlorine, and remember that that's diatomic. It reacts to form iron 3 ions. That 3 over there tells you its oxidation number and its charge, so it's Fe3+. And chloride ions, obviously are just Cl- ions. Now that isn't balanced yet. The question does ask us to balance it, but what I'm going to do is start by splitting them up into two half equations. So let's take the Fe2+ out, reacting to form Fe3+, and then separately I'm going to take out the chlorine, reacting to form chloride ions. Now what we've done here is to write them as two half reactions. They're not complete half reactions yet. They don't have the electrons in. They're not balanced. You can see we've got two chlorines and only one chloride ion there. So we need to do some work on them. But this is the idea, to separate the species out into two separate half reactions, and then using a particular method of balancing those half reactions, we will get an overall balanced equation, which we're going to do in a moment. Before we get there, let's just have a look at some of the rules for writing ionic half equations. The first rule here is to balance the number of atoms or ions on both sides by simply using balancing numbers. And secondly, once we've done that, we then balance the charges on either side by adding electrons as appropriate. Now there are a couple more rules for half equations that become slightly more complex, but for our work at the moment, those two will suffice. So let's have a look at this particular half equation. Tin 2, that 2 tells us its charge. So we've got tin is Sn, and it's 2 plus, and it goes to form tin 4, so Sn 4 plus on this side. So our first rule says balance the number of atoms or ions. Well, we've got one tin ion on the left and one tin ion on the right, so that's balanced. Secondly, balance the charges by adding electrons. We've got 2 plus on the left, 4 plus on the right. That's not balanced, so we need to add 2 electrons, which gives us 2 plus on the left, and 4 plus and 2 minus, which gives us 2 plus on the right. So that half equation now is balanced. Alright, why don't you have a go? These three that are given, in each case, write out the half equation and balance it. First balance the number of atoms or ions, then balance the charge so that we have a full half equation. So stop the tape, try and balance those, and then you can start up again. Alright. Let's have a look at this one. Lead 4 is Pb4 plus. Lead 2 is Pb2 plus. The number of ions is balanced. We've got one ion on the left, one on the right. We just need to balance the charges, so we need 2 electrons on the left. Alright, the oxide ion, that's the O2 minus ion. The oxygen molecule is the O2 molecule. In this case, we've got one oxide ion and 2 oxygen atoms, so we need to put in a 2 there to balance. We've got a charge of 4 minus on the left, 0 on the right, so we're going to need 4 electrons there to balance it. Then finally, the bromide ion, it's Br minus, bromine molecule, bromine again is diatomic, so it's Br2. So 2 atoms there, 1 ion there, so we need a 2 there to balance. That gives us 2 minus, so we need 2 electrons on that side. Right, let's now return to the problem we had a little bit earlier, where we had Fe2 plus ions reacting with chlorine to form Fe3 plus and chloride ions. So I split them into their 2 half equations. Fe2 plus going to form Fe3 plus. So to balance that, we need an electron on that side. Cl2, diatomic molecule, so we need 2 chloride ions. And that gives us 2 minus charge on that side, so we need 2 electrons on this side. Now, to balance these 2 half equations into a full reaction, what we need to do is balance the number of electrons. We've got 1 electron here, we've got 2 electrons there, so we multiply through by 2. Then in this reaction, we've got electrons being given off, and so the Fe2 plus is losing electrons, so that's oxidation, because oxidation is loss. Here the chlorine is clearly gaining 2 electrons, so that's a reduction of reaction. And what's important for you to understand is that these 2 electrons here that are being given off are the same 2 that are being received there. So there's an electron transfer happening from those 2 electrons across to those. When we balance them now, we've got 2 electrons on either side, so those cancel. Our overall equation then is 2 Fe2 plus Cl2 reacting to form 2 Fe3 plus 2 Cl minus. And that's now a full balanced reaction equation for that particular reaction.